Okay, so tonight we're going to talk about UML as a modeling language, or as the standard modeling language for object-oriented software development. And we also going to talk about, we're going to give an introduction to design patterns by example, and then relating that introduction somehow to Java. Meaning we'll take some Java examples from existing Java framework classes and so forth. So we're going to start with UML, and then we're going to finish with the design patterns introduction, which will give us a good segue into next week's topic, which is fully design patterns. So going forward, the only thing we will be talking about will be design patterns. And then we actually haven't started with the book. So next week will be the first time we will discuss topics from the book in detail. So for next week, you do have a reading assignment to read chapter 1 and 2. It is highly recommended that you do read chapters 1 and 2 before we start the discussion next week. The example that's used, or the case study that we will follow through starting next week, is designing a text editor. It's not an easy task, it's not an easy project, it's not a simple project, and rather it will help you tremendously if you get a head reading and familiarize yourself with the case study, familiarize yourself with the notations used in the case study. What is a glyph, what is a window, and so on. So this is just an advice that you do read 2 chapters by next week, and as the focus will be shifted to design patterns. We'll have the first introduction tonight. So let's go through UML, and we'll start with a reminder of the principles of object orientation. We'll summarize what we've been going through in the last 2 weeks. And then we'll dive into UML as a modeling language. The way we're going to approach UML today is from a use view, meaning how is it used and how do people look at it or view it, or how our designers and modelers look at it and view it. So we're going to look at the different views that, there are probably tens of views that people study when they study UML. They're all the same. At the end of the day, UML is nothing but the 12 diagrams that are used interchangeably for different purposes at different phases of the software development lifecycle. So we'll look at those views, and we'll explain. Our focus for this class would be the class diagram, because we need to understand how to basically structure classes to support ideas that we present in using design patterns. So each time we're going to talk about design pattern, we're going to look at the structure of the pattern, and the way we depict the structure is using a diagram, or the way we model the structure is using a diagram, which is a UML class diagram in this case. If we ever need to do a scenario, which we will, using some of the observable design pattern, for example, to explain it thoroughly, as a behavioral design pattern, we need to show the messages as they propagate from one object to another object. And for that, we use a different diagram, which is a UML sequence diagram. And we'll go through those today. So let's start with object-oriented analysis. Now, up before UML, before 1995-96, there were 3 popular modeling or object-oriented modeling techniques and methodologies used in the industry. There's the Greedy Bush, the Rumba, and the Ivar Jacobson. And they call them the 3 amigos. If you ever heard the term 3 amigos, these are the 3 amigos, basically Greedy, James, and Jacobson. And each one of them kind of focused on a particular phase or a particular topic in the software development lifecycle from an object-oriented perspective. And we've discussed the Bush method last week when we said Bush divided his phases into micro and macro processes. For example, at the micro development phase, define basically the set of tasks that we went through that basically matches or go along with what the waterfall model is, from communication to deployment. In the midst of doing all that, the set of activities that are included in the micro are identifying basically the classes and the relationships between these classes. And of course, each class you identify, you need to identify the behavior of the class, meaning you need to define the methods of the class, and then you need to define the state of the class as declared by its attributes. Now, so once you identify the classes, and then you need to refactor or factor these classes into objects. And we'll see how today, or not today, we've talked about some design principles last week. We said things can be done statically at the class level, or you can do the same thing, and we preferred it at the dynamically at the object level. And we said that the class basically is a static concept, and so is inheritance, because it's a static structure that cannot be changed. And we define static as things that cannot be changed after we compile. Rather, object composition and object aggregation is a more dynamic structure that we can use, and we have more flexibility in updating the structure of classes or our model as the application is running. So once you define the classes, then you go ahead and define the relationships between these classes. And those relationships determine or depict or mandate which objects can to talk to which other objects. And we're going to see there's a clear requirement in UML. No two objects can communicate without having a clear relationship defined between them, regardless of what the relationship is. We're going to talk about association, dependency, and other relationships today, but these relationships are must-have for two objects basically to communicate, send messages to one another. And then the macro development processes in the Bush method is basically you take these classes and you refine them until you are done with your design. The Ramba, on the other hand, he basically came up with what's called the OMT. All diagrams in your textbook, because your textbook was authored in 1994, before UML, all diagrams are written in OMT, Object Modeling Technique. It's a notation. It's box line diagram with the arrow pointing to certain things. We'll show some examples as we move along. But the Ramba says you define the object model, you define the dynamic model, and then you define the functional model. And then we do system level design and object level design. And you see Ramba took a more broader approach than did Bush, in that you define your object, your classes, and your relationship just the same way we did it in the micro development process of Bush's method. And then you go further and you define further object aggregations and objects behavior definitions. Usually objects behavior is modeled using a state chart diagram, for example, that describes the behavior of a particular object or the entire system. And then the functional model, we use an older method we used to use a lot in the 80s and early 90s. We call it the data flow diagram, which are a set of processes with data flows between these processes. Now, Ivar Jacobson focused on a use case approach. A use case approach is basically says we look at the system from your user's perspective and we derive what's called use cases. Use cases could be the basis for testing, they could be the basis for requirements, they could be the basis for the system scenarios. However, use cases by themselves do not depict much. We need further diagrams to elaborate on a use case. So think of a use case as a requirement that needs to be tested, and think of a use case as a snapshot of the execution of the program. One scenario, one possible scenario in the life of the program. The set of all use cases makes up the application requirements, basically. So Jacobson's method is used at early phases of the development life cycle, mainly at the requirement and communication phase, and Rumba's and Bush's methods are both used in basically all phases of the software development life, most with emphasis on design and modeling. Okay, so that's your summary for 1980s, 1990s modeling, object-oriented modeling approaches. And there comes UML. So UML, the first thing we said, I always try to get rid of this. Okay, UML said, why start? Why start from scratch? I already have 3 popular methodologies. Everyone is comfortable with. Everybody is used to them. The Rumba, Jacobson, and Bush's approach. So they took the same exact methodologies and applied them to UML. So UML is fully based on these 3 methodologies that we talked about. So there's 12 diagrams that are driven from either of the methods that we just discussed. But generally speaking, we talked about modeling last week, but why do we model? And these are just the 6 reasons that are stated in the UML summary or UML notation guides and the UML summary documentations that are found as part of the UML documentation. You know, a structure for problem solving, experiment before you drive further, and then you look at abstraction to ease the complexity of the application at hand, time to market, help decrease development costs, manage the risk of mistakes. Now, you could argue each and every point, you could argue otherwise, but nevertheless, the idea of modeling is to simplify things or to have something that's very complicated, very cumbersome, very unstructured, and kind of design it in a way that's appealing to the eye. So if you see this graph here, we have a torn apart city, and then the idea is to come up with a design and a modeling diagrams and pictures and so forth that makes that design more appealing and more so we can use it for communications with all stakeholders of the project. So to beautify the problem, abstract it further so we can understand it. Now, one thing you need to know about UML, UML is used at all phases of the software development life cycle without any doubts. There is a specific diagram, and each and every diagram probably you can use at every phase of the software development life cycle. So it's used for these 4 purposes. Again, this is stated at the UML documentation. It's a graphical language for specifying, visualizing, construction, and documenting anything that deals with software systems. And we have understood from our software engineering classes that building a software is not just programming. There's a lot more involved before we actually get to the programming phase. And unless you support an agile software development approach, and then you get to programming a lot faster than any other approaches like the waterfall software process methodology. Now, UML is the standard modeling language as of today, and it's adopted as such by the Object Management Group. That was done in 1997. So anything prior to 97 was either Jacobson, Rumba, or Bush's approach, or OMT, Object Modeling Technique, I think that's called. And then in 1997, they grabbed all those and made a UML out of them. The most recent version that I'm aware of is UML 2.0, which built on the concept of model-driven architecture, or also known as MDA. It's an area for research for those who are doing PhD or master thesis. This is definitely a topic that you may want to get on. UML is not a standard without any supporters. Almost every software company in the industry supports UML, and this is some of the companies that we have. A lot of these, by the way, don't exist today because of mergers and out of business and so forth. Now, if you were to study UML, For whatever reasons, you'll find an intensive line of documentations that you need to go through. The summary of these documentation is the UML summary, 700 pages that basically summarizes UML. Then semantics, notation guide, and then profiles. Profiles are extensions and additions to UML, because UML did not support everything. There's certain domains that require additional terminology to be defined in UML. For example, in the business modeling domain, there have been a profile to support business modeling notation. Also, UML did not have any support for database and database diagrammic, meaning modeling database systems like the entity relationship diagram that you're all familiar with. So UML introduced a profile for database support. So that profile extends existing UML notations and to support this new domain. The Corba facility domain, for example, is an extension to UML to support Corba. There's an XML extension. UML comes along with its own constraint language. They call it the OCL, or the Object Constraint Language. OCL is a language that, as the name indicates, it's used for constraints, exceptions, things that you want to add to the diagrams. I'll show you some constraints today as we see some examples. Always keep in your mind that UML is a language, unlike any other language, like Java, C++. It's made of two things, syntax and semantics. However, UML is not a programming language, rather it's a modeling language. A modeling means pictures and diagrams, boxes, lines and arrows and dotted lines and so forth. So the notation guide will be talking about these things, like what is a box? How do I define an interface or an abstract class in UML? How do I define a class in UML? Is it a box? Is it a rounded corners box? Is it a circle? And so forth. So that's what the notation guide tells me. That's what the syntax. Now, what does a class mean is defined in the semantics of UML. So if you look at the documentation, you got the syntax or UML syntax notation guide that tells me how to draw a diagram. And to know the meaning of the diagram, the meaning of a pointing arrow versus a dotted arrow versus a line with two pointers or two arrows is defined in the UML semantics itself. Okay? So the UML notation guide defines the graphical depictions of a diagram, while the UML semantics define the meanings of the taxonomy and terminology used in UML. What does a class mean? What does an interface mean? What is an abstract? What is a line going between a class and an interface? What is a dotted line going between a class and an interface with a pointing arrow? What all those things means is defined in the UML semantics. My definition to UML is 12 diagrams. How do you look at them? It really is dependent on the researcher. There have been research in almost all in the areas that you see in, not almost, all the areas that you've seen. There have been, everyone come up with their own classification. How do I classify UML diagrams? Some of them look at them from a functional, static, and dynamic perspective. Others looked at them from a, and I had it here, from a views, user view, structural view, behavioral view, implementation view, and environmental view. Others looked at them differently, from whether they're used within multiple objects or within the same object or the same class. This is the best diagram that depicts how these UML diagrams will fit in the picture. As you can see, I believe every diagram can be used at any phase of the software development lifecycle, and every diagram has some aspects of static, dynamic, and functional views in it. But purely, some diagrams, like the class diagram and the object diagram, they belong to the static view because the way you depict them, they depict some static notations. Now, take the object. The object itself is a dynamic concept. However, the object diagram is an instance of a class diagram, just like an object is an instance of a class. So that's why it remains in the static view. With the Venn diagram, you can see that the object diagram could also play a dynamic role. And from a dynamic perspective, we have dynamic. When I say dynamic, which the interaction of objects. In object orientation, this is what dynamic means: the working of objects to achieve a task. We have the sequence diagram, collaboration, and state chart diagrams. They're all examples or diagrams that are used to depict dynamic behavior. In a functional view, we have a use case diagram and an activity diagram. Whenever we talk about functional, we talk about functionality, which means we are defining requirements on the application. The way we define application, the use case diagram, which you already know that invented by Ivar Jacobson, is basically the most common requirement diagrams that it's used, and it is part of UML. Now, an activity diagram is a helper diagram. But what a helper means, we can take a use case and define it further, elaborate on the use case further using a using an activity diagram. So you draw a use case diagram. There's things, use case is very high level. To be more, to elaborate further on a use case diagram, it's actually the term that's used in UML code realization. To realize a use case, you use an activity diagram. You could also use a sequence diagram or a collaboration or a state chart diagram to elaborate further on the structure. Other views, like we said earlier, you can classify UML from a structural, usual, behavioral, implementation, and environmental view. Okay, structural and static goes hand in hand, and this is what we're going to start with: structural views of UML. Okay, the structural model. In generally speaking, when we talk about structure, we talk about classes and how are they relating to each other. That's exactly what we talk about when we talk about structural modeling. So when you define a class, you define a class and all of its members, including the behavioral members like methods and the state members like attributes. So you define everything that belongs into the class, and then you define how two or more classes collaborate. How do they relate to one another so that they can dynamically later on establish communication by sending messages, which means one object invokes the services of another object. For a structural modeling in UML, we use the class diagram. Class diagram is nothing but nodes and links. A node is a class, a link is a relationship between two classes. And link has a meaning, and there have different types of relationships as we introduce in UML. Take an example, the point class. The point class in UML, a class is, in UML notation, it states that a class can be represented with a rectangle with 3 compartments. The top compartment specifies the name of the class. The middle compartment specifies the attributes of the class, and the final compartment has the methods of the class. UML says the naming conventions in UML follows Java conventions. So a class name starts with a capital letter, and every subsequent word in the name must be capitalized. You can also use pure Java notation inside of the compartments to define, for example, a method. The way we do it in Java, you can do it exactly in UML, or you can use the UML notation, which is what you see in front of you here. Well, we'll talk about this in a minute, but the class diagram is defines the building blocks for the application. It's also sometimes referred to as the blueprint for the application. It tells me statically how all of my classes are structured and what are the relationships among these classes. By the way, the compartments, the last two compartments, are optional. So you can have a class diagram that shows only the class names. Quickly, the notation for the attributes is what you see here, or you can use Java. The first character that you see here depicts the visibility of the attribute, which is private, public, or protected, or even packaged. Tilde means it's a package, meaning this class have package visibility. All classes in the same package can see this class. And then the attribute name, in this case it's X, and then colon the data type of the attributes. And in this case, it's an integer. If the integer has a default value like 0, for example, you can say equal 0, and then you can say a constraint on the integer if you want. For example, you can say X is of type integer, default value equals 0. Between curly braces, you can say should be greater than or equal to 1. So you constraint, you put an exception, put a constraint to the range of values that are acceptable for X and or Y. Now, the methods, on the other hand, the same thing. You got visibility, which is the public, the name of the method move, and then delta X and delta Y. These are the parameters that are passed to the method. If the method has a return type, there is a colon, and then the return type is put next to the colon. In this example down here, we have an attribute that is public. The name of the attribute is total orders amount, and it is of type. It takes one parameter, which is an order type, an order object, and it returns a dollar object, and the constraints the total should be greater than 0 when this method is returned. You should never have a total that is less than or equal to 0. Okay, so this is how we do operations and attributes in UML, and this is exactly how we do class diagram. So going back to the point class, representation in UML is what you see in front of you here. Now this is at the class level. At the object level, UML says you don't need methods because they're objects, they're already running environment, and you don't need actual attribute names. Rather, you do need an attribute values to be specified in the object diagram. So in the object diagram, you'll see, for example, P1 is the object name colon point, the type of the object. You could also eliminate. You can just say P1 colon to indicate it's an object of some type, and then you can find out later what type of it of an object it is. Now, as you know, an object attributes have actual values. So the representation of the object model is really a snapshot of memory at a certain point in time. For example, take this code. We define P1 to be a new object. We get an object reference to point, and then we set X to 0 and Y to 0. Assume that X and Y are accessible. A better example would be to call set X and set Y to preserve encapsulation. But nevertheless, at this point, this is the object diagram for the program. This is the object diagram for the program, where P1 has X has 0 and Y has 0. If we move further and execute another command, which is a move command, by 20 and 15, the deltas, then at that point, this is the representation of the object model at that particular point. So you can see what I mean by dynamic now. An object is a dynamic because it changes values dynamically at one time. The class will always have this representation, but the objects will have different representation. It depends on when are you depicting the diagram at what point in the life of the program. Okay. All right, that's your 30 minutes introduction to UML and class diagram. Now, one of the most important aspects in class diagram is relationships. Relationships are referred to as associations in UML. Associations basically are must-have in UML for two or more classes to communicate. So no two classes can send messages to one another without having being able to without an association between them. Let's go back to this example. For example, this code here, this code that you see here, is usually sits in a client class, which creates the objects of type point and uses point. So there's another class here called the client class, and then the client class is allowed to send messages to the point class because there is a dependency relationship between them. They're related. This dependency relationship is what's called in UML an association. This is what I mean permit the exchange of messages, because the client class was able to send a move request or a move method or a move message to the point object to P1. So we said P1 move by this deltas, and the only reason we're able to do that because there is a client, there's a relationship between the client class and the point class that permits the exchange of messages. Now, that relationship could be bidirectional, meaning both objects, both classes can send messages to one another, or could be unidirectional, meaning in our case, it was a unidirectional because only the client knows about point. Point does not know or care about the client. So point object cannot send messages to the client object. If they were to do so, then they are heavily dependent, and then the arrows between them is bidirectional, meaning both classes can exchange messages to one another. So that's association. Association, especially the unidirectional, one direction, is a clear example of a client-server, or we sometimes refer to as dependency. A client sends a request to a server. The server fulfills the request without having the need to know about the clients. The clients know the server does not know or care about the clients. The clients usually serve multiple servers. So the server serves multiple clients, so the server is designed in a way to be loosely coupled and reusable. Okay, so a binary relationship is either shown in UML with two arrows, or you eliminate the arrows. If there's no arrows between two classes, that means both classes can send messages to one another and they are coupled and related. Take, for example, the class diagram you see in front of you. There's a student, a course, and a faculty. Between a student and a course, there is a relationship, an association. And the association is binary, meaning both objects of student class and both classes can send messages to one another. However, take the relationship between student and faculty. What you see here is you see an arrow pointing to faculty, meaning students can send messages to the faculty. So students are the client and faculty is the server. So the arrow always going into the server, to the server class. So the server fulfills the request, the faculty class fulfills the message, whatever it is, and then return responds back to the student because as a requester of the message. The relationship between course and faculty is binary. Both classes can send messages to one another. So what you see in front of you is a complete class diagram with a complete relationships expressed. Now, we're going to get fancy on a class diagram. We have an association, which is the line that connects two classes. An association could have a name. Take, for example, in this association between a student and course, it has a name called enroll. An association could also have a direction. You see this arrow? That's the direction of reading. So I can't read it course enroll student. It has to be read student enrolls in a course. Faculty teaches a course. And there is no name here between a student and faculty. These are not names of an association. These are referred to as association roles. What role does a class play in an association? For example, a student plays the role of an advisee in this relationship, while the faculty plays the role of an advisor in this relationship. A relationship or an association in UML could also have what's called a multiplicity. A multiplicity could be one-to-many, one-to-one, and so on. For example, one faculty member can teach many courses, and one course can have many students enrolled in it. If it's a one, it can be eliminated. It's optional to put a one here. And one faculty member can advise multiple students. However, one student can be advised by one and only one faculty member. So we know now the association name, the reading direction, the association roles, the role a class plays in an association. Other examples, what you see here, a person in a car. A person can own a car, rent a car, or drive a car. So the name could be different. It depends on the context that you are working with. A multiplicity basically depicts how many objects are required to participate in the association. One to many, many to many, and so on. An association role, for example, between an employee and a project, an employee can play multiple roles. In this particular example, an employee can be a manager or a user interface designer, these two lines, or a programmer. So there's three roles that one class, one object can play in a particular association. Is 1, 2, and 3. The name of the association, participate, and this is the reading direction for this particular association. An association can also have a constraint. In UML, a constraint can be written in English, like what you see in front of you, or can be written in OCL, Object Constraint Language, which is part of UML itself. For example, a person and a car. The name of the relationship is drives, so the constraint is must have valid driver license. That association cannot exist unless this constraint is evaluated to true. So no person can drive a car if they do not have a valid driver license. Okay, an association could also be interesting enough that it deserves its own class. So for example, the customer and a product, the association between them is order. Order is a structured object itself because it's a composite of other attributes. So you can have an order. We need a quantity of the amount, the items that were ordered. We need a date of the order, and we need the terms and conditions attached to the order. So since it's a composite, it can be a class itself. In UML, you do show a composite order class, or an association class, we call it, with a dotted line coming down from the association to the class in a class diagram, like what you see here in front of you. The order class is basically an association class. An association could also be reflexive. For example, an employee could play the role of a supervisor or a subordinate. And there is a relationship between a supervisor and a subordinate. You can show it by showing two classes of employees, or one class with a reflexive association. And reflexive means you turn back to the same exact class, like you see here, the relationship between a supervisor and subordinate. It goes back, it's like think of it, two instances of these same class could have an association themselves. Okay. Now, sometimes you need to qualify an association. This is not important. So let's look at this association example. This example basically has everything we talked about: a company and a person. And a company is a class, person is a class, a job is a class. This is how we read this diagram. A person has a job at a company. The person plays the role of an employee. The company plays the role of an employer. one person can work at many companies, and a company can hire many people. So that's a many-to-many relationship. A job is an association class because it requires a composite of salary. A job also is a reflexive class because a job instant could be a boss or a worker, so hence this reflexive association between them. So a job could play the role of a boss, or the job could play the role of a worker, depending on the instance itself. Okay, so that's your 15-minute summary of class diagram. One of the most important diagrams. You should have already learned this in CS 487 and other introductory classes, but I thought it's relevant that we talk about it here. We're going to use UML class diagrams heavily to explain the structure of design paths. Next, let's talk about specialization and generalization, mainly inheritance. Inheritance in UML is depicted in a class diagram with a diamond, or it's not a diamond, this is a pointing arrow that points from the subclass to the superclass, or the child class to the parent class, or as referred to in UML, from a special class to the general class, and hence the name specialization and generalization, and the is-a relationship that we talked about last week. So in this hierarchy, a student class is a general case, a graduate class is a specialized class. It inherits non-private members of the student class. Graduate class in itself is a general class for master and PhD classes. In UML, this models the is-a relationship. So a PhD is a graduate, a PhD is a student, just like any other programming language. The is-a supports the concept of polymorphism and the reusability, or creating a class from an existing class. This stuff we talked about last week. Now, what about an implementation of an interface? So we have an interface I that you see here, and then a class implements an interface using this notation in UML. Same thing as the inheritance, except it's a dotted line going down to the class that implements the interface. Remember, two interfaces can extend one another. If they do, then it's a straight inheritance relationship between them. Here's another example of inheritance or generalization, or the is-a relationship between vehicle, car, motorcycle, and truck. Truck is a vehicle, motorcycle is a vehicle, car is a vehicle. Yet another example of banking cards of yours. Inheritance is a static concept that applies at class diagram level. It applies only on pre-compilation. When we compile, we have the structure, it's fixed, it cannot be changed. The other structure that we talked about last week is aggregation and composition. A composition or an aggregation represents the whole part relationship. So the whole is made of multiple parts. So we can assemble an object from existing objects dynamically. Right now, we're talking at the object level, at the dynamic level. The best way to think of an aggregation is when one object contains another object. Think of a class that creates objects inside of it to make itself, or to make an aggregate of something, like a vehicle, make an aggregate of the wheels class, the engine class, the transmission class, and the body class. To create all these four inside of the vehicle class, then you got yourself a containment or a container relationship, which is an aggregation. Okay, so it's a whole part relationship. A window is a clear example of aggregation, because if you take the window that you work with here, you know, it has a title, it has bars, it has menus, it has everything. So everything is referred to as a window. If you destroy the window, everything will be gone. So that's an aggregation. That's a containment. One object contains multiple other objects, or one object is made of multiple other objects. An aggregation could be a composition or aggregation. A composition is a strong aggregation. the existence of an object is dependent on the whole, is composition. And however, if it's a loosely coupled, not loosely coupled, if the life of an object is not dependent, it's not containment, then we refer to it as an aggregation. Let's take some examples. A player and a team. In UML, we use a diamond to represent aggregation, like you see here, where the diamond points to the whole, not the parts. So a team is made of 9 and only 9 players in this relationship. Now here's a team and here's the players, and one team could be made of 9 players. Now this is the aggregation, this diamond, this hollow diamond that you see here. The reason it's hollow because if the team of all the players in the team quit, the team remains intact and they hire new players. So that's what the difference between aggregation and composition. On the other hand, composition, take the chapters in a book. One book is made of one or more chapters, so a book must have at least one chapter. And if you burn the chapters in a book, then the book is gone, and the same thing applies vice versa. If you destroy the book, the chapters are gone. So it's a strong aggregation. We refer to it in UML as composition. Composition in UML is showed with a filled diamond inside, is a filled diamond pointing to the whole object. And so here's composition. A player is made of player head, body, arms, and leg. If the player is terminated in a game, then all these objects will be terminated because this relationship depicts a composition because it has a filled diamond. Questions, concerns, please call me at 630-682-8794. Now, the other types of relationships in UML are referred to as dependencies. Dependency is another example of a client-server type of relationship, and the dependency could be directional or bidirectional and so forth. For example, an association, is basically a type of dependency because there's a client and a server. A client is requesting a service from a server. But the most common used type of dependency is the use relationship. So class C1, for example, depends on C2 if C1 uses the services of C2. How does the C1 use the services of C2? By simply C1 invoking objects against C2. So you create like our client of the point class. We invoke the move message against C2. So that's a use relationship. Our client class uses the point class. So there's a very common relationship in UML. Sometimes the dependency could have a refined meaning. So you qualify it with an extension. This is what we call an extension UML. So it could be an include, an extend, a define, a friend, a derive, a bind, or it could be a simple use relationship. So here's a summary of all the relationships that we talked about. And the syntax that is used for that particular relationship. So a relationship between two or more classes is just a line. We see aggregation and composition. You see here the whole part relationship. Generalization, meaning in UML it means inheritance or is a relationship. Dependency, by the way, is a dotted line pointing to the class that we use. So the client class uses the point class, should be a dependency relationship between them. Also the same notation is used, with the exception is it's a hollow triangle for an implementation when a class implements an interface. So here's a good example between order customer, corporate customer, and personal customer. This is a full UML class diagram. So there's a dependency relationship between the order and the customer, or a use relationship. The order class uses the customer class, and one customer can have many orders, The customer class cannot send messages to the order class, and the order class can send messages because of the arrow, because of the direction of the dependency. There's an inheritance or a generalization relationship between customer, corporate customer, and personal customer, and a specialization generalization type of relationship. Any questions? Okay. So that's an hour introduction to UML and UML class diagram. Next, we're going to talk very quickly about the remaining diagrams. I don't believe I will be using these diagrams in this course. We've discussed those in details in CS 445, the use case diagram and the behavioral diagram. So I have a slide or two about each one of them. We finish them and then take a break and we come back and we talk about an introduction to design patterns. So a use case diagram is a diagram that depicts the functional requirements of the application. So it's used at the initial phases of the software development lifecycle. That diagram says I can divide the system into a set of scenarios, or they call them use cases. A use case diagram is what you see on the left-hand side of this slide. There's a box that represents the system, this box. It represents the system that we are developing, and anything inside the box is what we develop and we have control over, and anything outside the box is our users of the system. A user of the system in UML use case diagram is shown with a stickman notation, which is what you see here. That's a human user. If it's a machine user, we use a box to depict that type of user. A line between a user and these ellipses inside of the system are use cases. These are snapshots or scenarios in the life of the execution of the program. And a line between a user and a use case, that means that user deals with this use case. A user can deal with multiple use cases, and a use case can be dealt with by multiple users as well. Now, a use case is very abstract. It tells the requirements at 30,000 feet, so we need another diagram to basically realize, and using the term that's used in UML, realizing a use case. So we take this use case and we realize it in UML with a narrative, simple English. We can explain what the use case does, or we use another UML diagram we refer to as the activity diagram, which is a flowchart type notation, which depicts the execution of the use case top down, command by command, with the notation that you see in front of you. Or you can use a sequence diagram, which we will see in a minute. Okay, so here's an example of a use case diagram. It's a telephone catalog, meaning you can call in and make an order. So the system has 4 use cases: check status, place order, fill orders, establish credit. And the system has 4 different types of users outside that interact with the system. There's a customer user, a salesperson, a shipping clerk, and a supervisor. And the customer user can check status, can place orders, and can establish credit. But the customer user cannot fill orders. Fill orders is done by a shipping clerk. A salesperson can also check status, place order, but they cannot establish credit. A supervisor can only deals with established credit. The supervisor determines if a customer establishes a good credit or a bad credit, and so forth. So that's a use case diagram. Now, now you know what I mean when I say 32,000 feet. Now, check status, yes, but what objects, what classes participate in that, how does the check status work, and so forth. For that, we use the help of other diagram or narrative written in English. Here's another example of a use case diagram. Okay, next, behavioral diagram. We have 2 types that we study, that we quickly introduce today, is the sequence diagram and the state chart diagram. A sequence diagram, basically, it takes a use case and tell me in time what happened. What is the exact scenario for that requirement or for that use case? So it's mainly used to realize a use case or implement a use case, like others puts it. And what it does is basically it places objects in a timeline, like in this particular example. We have objects, producers, synchronization aspects, scheduling aspects, and bounded buffer object. And these objects that you see, everyone has a timeline going downwards. So down, as you go down, it's time. And messages propagate from one object to another object in time. So at the beginning, for example, the producer puts an item, a request that it needs to put an item to the synchronizer. The synchronizer checks, increase the number of items. You see this here. This means the synchronizer is doing something, which is it increases the number of items, and it sends an event to the scheduler. Say this guy needs to add an item to the buffer. The scheduler has a requirement that only one writer at one point of time can write to the buffer. So it checks, and it increases number of writers by one, and then it sends the event. If everything is okay, it sends the event to the buffer. The buffer does the actual writing, and then it returns back done. And when it's done, the scheduler needs to deduct the number of writers by one, and that message goes back to the synchronizer, and then that's it. Or actually, it ends there, which means the item has been added to the buffer. Okay, we're going to talk about this example a lot. We're going to actually use it as a driver for homework assignments, the programming home assignments, starting probably this next week. Yeah. Here's another example of a sequence diagram. We have an order entry window, which is an object. An order is an object. A delivery time is an object. And notice in this particular diagram, we're using objects. Sequence diagram is a behavioral diagram. Behavior means object, dynamic. So does the state chart diagram. Okay, so what you see here is an object. You see how we notation for an object with the colon, and you can also put the class name after the colon to depict it's an object with only one compartment, which is the attribute values. Nevertheless, in timeline, in UML, an object like this, a line, dotted line going down, or some people put it a straight line, it means the object is dead. It's not created. It's not instantiated yet. When it's a box like this, or a rectangle, a long rectangle like this one, that means the object is instantiated and is doing something. Is running an operation. In this example, this object sends the prepare method or message to the order object. The order object, notice, at this point it was not created, at this point here, and then when it got the message, it got created, and then it stopped processing, and then sends an object to a delivery item. You could also remove the dotted lines that you see here and drop the object down to this like we did here. Or you could put this on top and then do a dead line, meaning dead, the object doesn't exist, and then eventually when it gets the message, it gets created. Okay? And then if there's an out stock, there's an out stock, and then the object terminates, and so on. Do you see how this depicts behavior in time, and it shows messages as they propagate from one object to another object to achieve what? One scenario, or multiple scenarios. A scenario is basically declared in a use case diagram. So now you have a complete view of the application almost. You have the structure view in a class diagram, and then you have a requirement view or a functional view from a use case diagram, and now you have a dynamic view from a sequence diagram. So all the views are now making sense, because putting together you have a complete description of an object model. Okay? All right. Let's talk about state charts. State charts are invented by David Hurrell. They were called state machines before UML, and then UML adopted them as the dynamic behavior description for one object. If you notice a sequence diagram, it involves multiple objects. It describes the behavior between multiple objects. A state chart diagram mainly used to represent one object's behavior. So if you take this example, a lamp, and you have two states, two buttons. When a button on is depressed, the light goes on, and when it's depressed, the light goes off. It doesn't work, my automation doesn't work very well, but at least the light goes on is pretty nice. There you go. It is on. The sound is delayed. Okay, so that's what automata, what we refer to in computer science as automata. Let's go back to the lamp. The lamp could be in any of two states, either on or off, or dead, or meaning doesn't exist, or broken. When you are in off state, someone sends an event on. How do I send an event? In the case of a lamp, it's a physical event. We turn the switch on, so we transit from an off state to an on state. While we're in transition, we can do things. We can execute a method, we can send a message, we can do whatever we want to do. But in this particular case, we don't do nothing. We just switch back to the on state and turn the lights on. While I'm in on state, I can press the off button and transition back to the on state. While I'm in on state, I can press on, nothing will happen. Same thing if I'm in off state, I can press off, nothing will happen as well. Now, the question would you ask yourself, why did the lamp go on when the on button was pressed while I am in off state? The answer is because it's automata. Automata means an object, or automaton actually, but the end is not pronounced. It means the object remembers its states. Okay? Remembers its states. The lamp only went to the on state because it was an off state. If the lamp was an on state, it wouldn't have done nothing. And that's what automata is all about, is objects remembering their state. And your behavior is dependent on the state that you're in when an event is triggered. An event could be anything from a method invocation to a timer to a thread execution to anything that could possibly happen. Now, in UML, a pseudo state, which is an initial state, is shown like this, and also there is an end state which shows like this. There's two circles, one, and there's another circle above that, and there is shadowing. It's the same thing like this, but there's a white circle in the middle. That means terminating the state. Okay. Now, the last thing in UML, I mean, there's other diagrams, but these are the most commonly used diagrams today. For example, the environmental view, or sometimes referred to as a package diagram, is when you deploy the application to the customer, how is it going to be deployed? How is it going to be deployed? So in there, because you could run multiple machines, multiple CPUs, you can have servers, you can have nodes, you can have connections, you can have whatever you want to have. This diagram that you see in front of you is what we refer to as the environmental view, or as the deployment diagram. It means in this particular, there's two nodes, node 2 and node 1. They could be distributed, they could be different machines. And in node 2, we put the first component or package in UML or component. A package is multiple classes. That's what the component or package is, with known interfaces. And in the node 1, there are two packages, which are referred to as component 1 and component 2. This is how we do a component in UML. It's a box with interfaces coming out. Because what is a component? it's a logic, a business logic, with API interfaces to the outside world. So if you need the services of a component, you can only get to them through that particular link. Okay? All right, so this is referred to as a component diagram, and let's stop here. We'll come back and talk about something else.